Hello, hello, hello. This is Nicholas on this lovely Wednesday afternoon. Wanting to first apologize for my relaxed uploading schedule. It will get better. And then secondly, wanting to tell you ask you what's faster than a calculator? And the answer, of course, is a CalcuNow. Anyways, what I really wanted to talk to you today about was infinities and circles, and that seems like a pretty broad topic. So specifically, I want to introduce the idea that some infinities are bigger than others. And bigger is also one word when I first learned this that I had to struggle with a little bit. What exactly do you mean by bigger? And so I'm going to really emphasize that aspect. So some infinities that are pretty common that I'm going to talk about in this video are, well, one infinity is the natural numbers, which is usually abbreviated as n. And that's just usually includes 0, sometimes not. 0, 1, 2, etc. We have the integers, which is just the naturals and their negative counterparts. So that's with a z. For whatever the reason, we abbreviate it with a z. And that's like ... -2, -1, 0, 1, 2, ... We have the rationals, which is abbreviated with a q. I don't know who came up with the abbreviations. And that's just anything of the form p over q, where p and q are elements of the integers. In other words, p and q have to be integers. So, and then kind of separately, and I'll detail why I do this separately later, we have the reals, which is r. And that's, in one sense, right, it's any number that has like a valid decimal expansion. So, that could be like now things like pi, e, the square root of 2, and so on. But in a different sense, which I think is more helpful, we can think of it, right, as like R1, in other words, 1D. In other words, all numbers that span the real number line from -infinity to infinity. So now why did I talk about these separately? Well, what I'm going to show actually is that these three infinities, the naturals, the integers, and the rationals, really aren't all that much different. And it's the reals that's the real kicker. They are infinitely more infinite than these infinities. Now, I said bigger. Now, what did I mean by bigger? How is one infinity bigger than the other? Well, how we kind of quantify what's known as the cardinalities of different infinities, in other words, like the sizes of different infinities, is through bijections. So a bijection is a property of a function. If a function is bijective, it takes a unique input and it maps it to a unique output. So no two different inputs can yield the same output. And so if we can come up with a way to map every unique natural number to, say, every integer, then we've shown that those two infinities are the same size, because the function that does that mapping can, since if they're both the same size, then there exists a function that can map every number in this set to every number in that set. That's how we go about kind of determining in a more rigorous sense, which would be talked about in like real analysis, how infinities are bigger than one another. And so with the with the natural numbers and the integers, that's a pretty easy thing to do. So if I let me write out a bit more of those. So 0, 1, 2, 3, 4, 5, 6, 7, 8. I'll stop at 8. And then, so that's the natural numbers. And then now for the integers, I'll write it like this: 0, 1, -1, 2, -2, 3, -3, 4, -4, so on. And so the question is, well, how can we map every element in this set to every element in that set? And the answer is, well, pretty obviously, right? We can just take every, say, even number and map it to the negative of the integer counterpart. So in other words, let's say we come up with a function, f of n, that maps every natural to every integer. What would that function look like? Well, f of n, it would be a piecewise function. If n is even, then f of n would be what? Well, 0 goes to 0, 2 goes to -1, 4 goes to -2, 6 goes to -3, 8 goes to -4. F of n is going to be then -n/2. If n is odd, then f of n equals what? So 1 goes to 1, 3 goes to 2, 5 goes to 3, 7 goes to 4. So what's going on there? F of n is always going to be, right, it looks a bit more obvious here, right? If I take 5, I add 1 to it, and then I divide that number by 2, I get 3. So f of n is going to be, n plus 1/2. And boom, there is our function, f of n, which is bijective, because its two constituent piecewise parts are bijective, because they're functions, right? These are indeed functions. These are just lines. And so what we've now shown then is that the naturals and the integers are the same size of infinity. They're both what we call countably infinite. And the name from this comes from the fact that we have essentially devised a way to come up with, or we've devised a method to count all of the integers. Now, it would take an infinite amount of time to count all of the infinite amount of integers, because there's infinitely many, but we've devised a method such that if we were given an infinite amount of time, it would be guaranteed that we would not miss a single integer, right? If I go 0, 1, -1, 2, -2, 3, -3, 4, -4, so on, continuing that method of counting the integers up, then I will have listed every possible integer. I would not have missed any integers. And of course, this is trivial in the case of the natural numbers, but right, 0, 1, 2, 3, 4, 5, and I go on about that way. I will have not missed a single natural number. And so that's where the name countably infinite comes from. It's not so much that you can, like in a human's lifetime, you could of course never count them all, but it's the fact that in an infinite amount of time, there's a method such that you can count them all. Now, for the rationals, it does get a bit more complicated to show that the naturals, the integers, and the rationals are all the same size of infinity. In other words, that there still exists a bijective function, f of n, that maps every natural number to every integer. But it can be done. Now, I'm not going to so much emphasize on the function this time as I am the method on how we count the rationals. In other words, I'm going to kind of emphasize this here, the fact that if we can devise a way to list out all of the rationals such that we could count them all in a finite amount of time with while being guaranteed to not miss any, then that would show then that the naturals, the integers, and the rationals all have the same, quote, cardinality or size, and they're all countably infinite. So, right, maybe I had to get a little nifty here on how I wrote this set of the integers, right? Because originally I wrote it like this, and then I wrote it like that. But I think you can see that writing it in this way is especially more useful, at least for our purposes. So how can I write the rationals in a way such that when I list them all out and I count them all, and of course in an infinite amount of time, I will have guaranteed not to miss any rationals. And well, it goes like this actually. I didn't want to try to draw the arrow myself, so I did get a picture. But the way it works is pretty simple, right? We start with 1 over 1, and then on each row, we just add 1 to the denominator. So 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, so on. And then on each column, we add 1 to the numerator. 2 over 1, 3 over 1, 4 over 1, 5 over 1, and so on. And what we can actually do is, right now, if I were to continue this list this way and this way, I will have encompassed all of the rationals. Now, of course, it is technically all of the positive rationals, but, excuse me, if you wanted to talk about the negative rationals too, right, it really wouldn't be all that different. You would just slap negative signs on all of them. So for this case, we can just talk about the positives. Now, this list is all inclusive, right? This lists every possible rational number because of the way we've designed it, right? Because of the fact that the rationals are built on the naturals, and we have systematically designed our rows and our columns to include all of the naturals, then we will include all of the rationals. And now how can we go about counting those? Well, again, we couldn't just count like this, right? Because then we would just keep on going down this column, and we'd never be able to count all of the rest of this stuff. And likewise, we couldn't go just along this row, because this row is infinite, and so it continues on forever. And so if we just went along this row, we'd never be able to count, or even in an infinite amount of time, we'd never be able to get to any of this stuff. And so thinking about it like that, that implies that we kind of need to do some sort of zigzag in the way we count, right? And that's exactly what we're going to do. We're going to count, we're going to say 1 over 1, 1 over 2, 2 over 1, 3 over 1, 2 over 2, 1 over 3, 1 over 4, 2 over 3, 3 over 2, 4 over 1, 5 over 1, 4 over 2, 3 over 2, 2 over 4, 1 over 5. And we're going to continue on that zigzag, right? Like this, like that, like that, like that, like that, and so on, right? And so in doing this, while, yes, all of the rows and all of the columns are infinite, we will be indeed counting by the design in which we count, right? This clever fact of moving diagonally instead of just straight across one way or the other allows us to list off every possible rational in an infinite amount of time, and we'll be guaranteed to count them all. And so listing them in this way, right, if I were to write the set, now if we're going back to how I talked about it in this case, if I were to write the set as, 1 over 1, 1 over 2, 2 over 1, 3 over 1, 2 over 2, 1 over 3, 1 over 4, 2 over 3, 3 over 2, and then 4 over 1, and so on, right? If I didn't have this picture in the back of my mind as to how I'm writing those numbers, this would seem like, whoa, what are you doing? But when you think about it in terms of this picture here, it makes a whole lot of sense. And so, so now, if I write the naturals now, 0, 1, 2, 3, 4, 5, etc. This way of writing the set will include every natural number. This way of writing the set will include every possible rational number. And so we can map each unique natural number to a different unique rational number. And therefore, there exists a function f, which is bijective, that maps every natural to every rational, and therefore they're countably infinite. Now, that might take a moment to swallow, and it always seemed to me like the rationals were just barely countably infinite, right? You know, it was pretty easy to do it for the integers, but it is kind of clever to do this for the rationals, you know, and it seems to me like, well, at least when I first learned this, like, yeah, well, I mean, the rationals, they just, you know, they seem so much bigger than the naturals. But in fact, they really are the same size. They're the same cardinality. Now, the naturals, though, is where it really starts to get interesting. In fact, as it turns out, there are more. I said naturals. I meant the real numbers. It turns out there are more real numbers between, and you could actually pick anything here, but I'll say between 0 and 1 than natural numbers. In other words, there are more real numbers between 0 and 1 than there are the total infinity of natural numbers, and therefore the total infinity of integers, and therefore the total infinity of rational numbers as well. Now, the mathematician who showed this also came up with this way of devising writing down the rationals. Georg, they spelled his name wrong. It's actually Georg. There's no E. It's Georg Cantor. And this is known as Cantor's diagonalization argument. In other words, what he sought to show was that there is no such function that is bijective, that maps every natural number to every real number. And so the way he showed this was really pretty nifty. He said, okay, you know, write down a list that supposedly contains every possible real number from 0 to 1. And then he showed by contradiction that list is actually not all inclusive. In other words, he said, suppose you have a list of all real numbers between 0 and 1. And then he showed that, well, that's impossible. You can't. And so therefore there is no such bijective function. The way he did this, he said, okay, come up with a list on your own that includes all possible real numbers. So, all possible decimal expansions from 0 to 1. So 0, let's come up with just some random decimals here. 0.130578923 0.27066358821 0.312578037 0.4669999382 and so on. Suppose that list contains every possible real number. And then he said, okay, well, now go along the diagonal. This diagonal here. This diagonal contains the first decimal, the first digit after the decimal of the first number, the second digit after the decimal of the second number, the third digit of the third, the fourth digit of the fourth, and it would really have the fifth of the fifth, the sixth of the sixth, and so on. And he says, well, what you can do is devise a new number that can be computed by just taking the digits along this red diagonal and just adding 1 to each of those, right? So our new number would be 1 plus 1 gives us a 2. Now 7 plus 1 gives us an 8. 2 plus 1 gives us a 3. And 9. If it's a 9, say, move it down to an 8. Doesn't really matter. If you made it a 0, like 10, or if you made it 8. Doesn't really matter. And then we would really have another number here, another number here, if this list were infinite. So I'll just make those up, whatever they are. And now this new number right here cannot possibly be on our list because it has to differ. It has to. The way it was created, it has to differ in at least one spot, in at least one digit from all other numbers on this list, even if this list is infinite, because it was designed that way. It has to at least differ by one digit, right? Because this first digit isn't the same. This second digit isn't the same. This third digit isn't the same. This fourth digit isn't the same. And so at least one, if not more, of the digits on this new number has to be different from the digits on all of the other possible numbers on that list. And so therefore, we've created a new number that is not on our infinite list of real numbers. And so therefore, there is no possible way in which you can list the real numbers from 0 to 1, or really from 0 to what, I mean, you could have picked any bounds here. I just chose 0 and 1 because they're kind of natural. Not natural. They're nice numbers to work with. And so there's no way to write out the set of reals, in this case from 0 to 1, such that in an infinite amount of time, you could count them all. Because we can always come up with a new real that's not on our infinite list. And so therefore, we've shown that the real numbers are what we call uncountably infinite. Now, that means that the reals have a different cardinality. They're bigger. The infinity of reals is bigger than the infinity of naturals, integers, and rationals. All of them. And so one other way I'd like to illustrate this is actually with a really cool paradox involving circles, right? I mentioned circles at the beginning of my video. So let's have a big circle here. Okay. And now this circle has let's call it a unit circle so that its circumference is pi. Now, let's say I pick a point on this circle here, and let's say, maybe I draw it straight through that radius right there. I pick this point, and I just toss it. I just get rid of the point, right? And then let's say I move. Right now, the total circumference of the circle, C, is pi times 1 squared, or pi. It's important to note that the circumference is pi. In other words, it's irrational. And now, let's say I move 1 unit along the circumference of the circle, right? So if the whole circumference is pi, I go, maybe like up to here, a little bit less than a third of the way. And now the point that I threw out, which is now here, I'm going to now put it here, and I'm going to now throw out this black point up here. And then I'm going to move another unit along the circumference of this circle, and I'm going to throw out now this point. But then this point here that I threw out, I'm going to move it and put it in place of the point right here that I just threw out. And then I'm going to move another unit distance along the circumference of this circle, right? And I'm not going to end up at the same point because I've now moved 3 units, but the circumference is about 3.14 units. And I'm going to take this point and I'm going to throw it out. But then I'm going to take this point here that I threw out right here. I'm going to take it and put it in place of this point right here that I just threw out. And now hopefully you can see where this is going. I'm going to go another unit. I'm going to take a point, throw it out, replace it by the previous point, and so on. And what we have in essence done now is effectively removed a point from the circle, right? If I continue this infinitely often, realize that I will never land on the same point twice because the circumference of pi is incommensurate with the unit distances in which I'm traveling. In other words, no multiple of pi is a natural number, right? No multiple of pi, because pi is irrational, will get me on one of these points that I've thrown out, removed, and then replaced back by a previous point. And so I have essentially removed a point from this circle. But I have not changed anything about the circle because I'm replacing that point. And so the excuse this pun, but the point that I want to illustrate here is that you can actually remove countably infinite many points from a circle and still be left with the same circle, right? If I started at a different point on the circumference of the circle, like instead of starting here like I did originally, say I started anywhere here, and then I kept my game up. I moved the unit along, threw that point out, but then put it over here, threw this point out, but then put it over here, threw that point out, but then moved it over here, and so on. I've just removed another point from the circle. And I could keep doing that because of the fact that pi is incommensurate or not a scalar multiple of, or not any multiple of pi is not a natural number. And so this is kind of analogous to the difference between countably infinite and uncountably infinite, right? I can remove countably infinitely many points from this circle and not change anything about the circle. But when I move uncountably many infinite points from the circle, that does change, right? Because let's say I remove all points in this region here. Well, this arc here is, it's an arc. It's a line, not a line segment, but it's an arc. And an arc is a one-dimensional construction, which is composed of infinitely many zero-dimensional points. And zero-dimensional points, we can kind of think like numbers in these countably infinite sets. Whereas intervals along the circumference of this circle, in other words, an arc, we can kind of think of like a 1D space. We can kind of think of it like the real number line, except it's not really a line. In this case, it's an arc. So in this way, it kind of made things click for me, this analogy that, well, yeah, the reals are going to be different from the naturals fundamentally, because the reals really are about intervals. The naturals really are about discrete points. And a point is just not the same thing as a line. And with that, we're done.